Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
You see that the topic is quite hot in the audio industry. Can we have coexistence between Wi-Fi, white spaces, and wireless microphones? And without further ado, I'll introduce the two speakers for tonight. This is Ranveer Chandra. He's a senior researcher in Microsoft research here in the Mobile Computing Research Center. As pretty much everybody in this building with this rank, he has published multiple papers and has multiple patents. To be precise, more than 40 patents, 12 of which are granted. And he basically has multiple awards, but one of the most prestigious is being one of the 35 young inventors granted by MIT Technology Review every year. The other speaker is George Nychis. He is a PhD student in Carnegie Mellon University and was intern here in Microsoft Research twice. Just to let you know, just to be once during your PhD studies, intern here in Microsoft Research is a lot. And he has this opportunity twice and earned the being intern here, so they will present their work. Without further ado, Ranveer, you have the floor.
Hi, thanks for coming over. Ivan said I'm Ranveer Chandra, and we have been working on the Whitespaces project for a very long time. Since 2005 is when we have been working on it. And this work is jointly done with George. Thomas Moscibroda, he was my collaborator here. He moved to MSR in China. We still collaborate a lot, and Ivan taught us all the audio parts of what I'll be talking about today. I'm mainly a wireless guy. Audio is something that I'm learning just for this, because Whitespaces did impact the audio industry significantly, and we had to consider this problem in order for the rules to be adopted. So by the way, this is a small crowd. Feel free to just raise your hand at any time and ask questions. Most of the talk is wireless. I can understand if you don't have the background, but don't think it's a stupid question. I'll try my best to explain it. So first I'll begin by motivating the need for white spaces. I know from your perspective, it's all evil. It's going to destroy the wireless industry. For the audio industry, from our perspective, for wireless guys, this is big. White spaces is something which we have been struggling for a long time. And why is it important? The reason is there is this thing called the big spectrum crunch that the FCC in its broadband plan called the impending spectrum crisis. That is, the amount of good spectrum that can be used is limited. Qualcomm, for example, if you ask them, there's a report which I read where they say the best part of the spectrum that you can use for wireless communication is from 300 megahertz to 3 gigahertz. That is the amount of spectrum that is good for mobile communication, for devices that are mobile. So the amount of good spectrum is just that much. And within that, over the last few years, there has been a huge proliferation in mobile devices, phones, tablets, whatnot. Not only that, the amount of media demand, the demand for video on these devices is growing significantly. These are just some of the forecasts, and this is iSupply, and most of the people are watching YouTube and Netflix. And as you can see, this has been in the news all over. This is Cisco saying that, well, the amount of data traffic will double every year. De La Vega, he's the CEO of AT&T. He says, well, something needs to happen soon. We are running out of spectrum. And this is something which is all over. Even now, you'll keep hearing this more and more, reading about this in the news, that the amount of usable spectrum is limited, and we need to do something more. So CTIA, which is the organization of the carriers, they approached the FCC and said, you know what, give us 800 megahertz of spectrum. That's what we really need by 2015 in order to meet user demand. The FCC, well, said 800 megahertz between 300 megahertz and 3 gigahertz is a lot of spectrum to ask for. So the FCC pushed back and said, we'll do something and try to get you 500 megahertz by that time frame, right? The interesting thing is, if you look at the next chart, this is the spectrum allocation chart for the US. This is from 3 kilohertz to 300 gigahertz. Nearly all of it is allocated. Where does the FCC get 500 megahertz from? That too from 300 kilohertz to 3 megahertz, 300 megahertz to 3 gigahertz. Where does it get that spectrum from? So that is where we started investigating a new technique. This was back in 2005 when there was no rules around it. We said that instead of statically assigning spectrum for purposes, so for example, assigning certain part for TV, certain part for cellular, can we come up with a new spectrum use paradigm? That is, we'll figure out which part of the spectrum is not in use and use that for unlicensed communication. And the first attempt that we made was at the TV spectrum. This is the broadcast TV spectrum where wireless mics operate as well. So in this chart, this is log scale, by the way. Each row is log scale. In this chart, these are the portions where the broadcast TV exists. And this is where Wi-Fi operates right now. So there's, not to take the absolute measure, but still there is more than 3 times the amount of spectrum that is used by broadcast TV. So the first question we asked was, can we use this TV spectrum that is not in use by TVs at that time for wireless communication, for unlicensed communication? And this is, the reason we went after this was that there is this analog to digital TV transition that has happened in the US and is happening worldwide. In the US, it happened in summer of 2009, Japan in 2011, and so on. Every country is moving from analog TV to digital TV just because it is so much more efficient to send data over the TV bands, over digital TV. So the FCC in 2008, it announced this historic ruling which said you can use the unused TV channels for Whitespace, for unlicensed communication. And this was, as you can expect, was in the news all over. Every newspaper you could read talked about this as the next big thing, because now all of a sudden you had so much more spectrum to connect to the internet, right? I know people were not talking that much about wireless mics, but we'll come to that in a bit. So before I get into that, what are the white spaces? Just defining it more clearly. So suppose this is, the x-axis here is frequency. That's where Wi-Fi operates right now, 2.4 gigahertz and 5 gigahertz, 802.11g and 802.11a in the 5 gigahertz spectrum. This is from DC. So, and this is where TV exists, of VHF up to 216 megahertz and 470 to 698, essentially. That's where UHF TV broadcasts exist. And this spectrum is where right now all the wireless mics in the US operate. The interesting thing is, even though this frequency is allocated for TVs and wireless mics, not all of it is in use at every place. So what we did was we took this spectrum analyzer, this is a RF spectrum analyzer. We took it to one of the houses. This was an intern who was here back in 2006. She took the spectrum analyzer to her place. She measured the spectrum occupancy across time. And this is what we found. This is a UHF part of the spectrum. And a lot of the spectrum, even though it's allocated for TV broadcasts, is not in use. This varies at different places. In Redmond, it is certain channels. If you go to Seattle, it's a certain other set of channels that are not in use. And these are what are defined as white spaces. That is, allocated but not used TV spectrum is what we call as white spaces. To give you some more background about white spaces, there are 50 TV channels. Each channel is 6 megahertz wide in the US. Most other places in Europe and Asia, it's 8 megahertz wide. But most of the other principles still hold. So then the next question, I just defined what are white spaces. The next question is, why should we even care? Why is this so cool for the wireless industry? So the most important thing is, well, this part of the spectrum offers, well, much, much more spectrum to send data bits on. There is a spectrum crunch going on. Given that crunch, getting any more spectrum is very, very useful. And over here, you could get up to 3 times that spectrum. That's up to close to 300 megahertz of spectrum can now be made available, depending on where you are, for data communication, right? So just having much more spectrum is so cool. But the bigger advantage is that in this part of the spectrum, because it's in lower frequencies, you get much more range. Signals propagate much, much more. Theoretically, it's about 4 times the range of Wi-Fi. We've done measurements where it's even more. I'll get to those measurements in a bit. So combine these 2 properties, all of a sudden you can think of so many new applications which until now were not possible. For example, rural broadband, citywide meshes. Google deployed this citywide mesh in Mountain View. It wasn't a big success. The big reason is you put up a router on the lamppost, and you don't get a signal inside the house because the windows add huge amount of shielding. The 2.4 gigahertz signal just don't propagate as much. In the lower frequencies, your signals just get into the house much more easily. So that's why you can see why the wireless industry is so excited. Carriers are excited because now they think now they can offload a lot of the data from the phone onto the Whitespace network. Then you can think of many more scenarios, like people can deploy citywide networks to support an alternate voice network, say Skype-related something, right? So there are many applications. One just has to start running their mind, and they can come up with many new applications over this part of the spectrum. So with this in mind, so we know the benefits of this part of the spectrum. So we went out, this was the first question we asked is, okay, what does it take to build a network over the white spaces? Suppose we set up a tower, we had so for example, those two devices sitting right there, they are both white space devices. So what does it take? So these are software-defined radio-based. We are still getting to the ASIC design. But then the question was, once you have these devices, how do you really form a white space network? What are the challenges? So that's what we set out. We set out asking this question long back. And the first thing that arose was, why not just reuse Wi-Fi-based solutions? Why won't Wi-Fi work as is over the white spaces? So there are three key differences. I won't dig too much deep into it because I know you're not wireless people. But if you're curious, you can ask me any questions here. So the first difference when compared to Wi-Fi, the Wi-Fi spectrum and white spaces, is that this spectrum is fragmented. In Wi-Fi, I don't know how much you know about Wi-Fi, but you have channels 1 through 11, right, in 2.4 gigahertz. A lot of you must have configured your router to operate on one of them. You can operate on any one of those channels, and that's contiguous part of the spectrum. In white spaces, portions of that spectrum might be occupied by TVs or by wireless mics. You cannot use that spectrum. So the spectrum, in turn, is fragmented. You don't have one chunk, parts of it. So for example, there's one chunk which is 4 channels wide, one which is 2, one which is one channel wide. So each channel, as I said before, is 6 megahertz wide. And so this is what we call as the first difference, which is fragmentation, right? And we measured this fragmentation in different parts of the US. Blue is urban, red is suburban, green is rural areas. As you can see, in urban areas, there are lots of TV channels. So there are lots of small fragments of TVs, the small fragments of channels that are available, either 1 fragment wide or 2 fragments wide, mostly. In rural areas, where there are very few TV channels, you have these chunks which are more than 6 channels wide, which are not in use, so available for white space communication. So because each channel is 6 megahertz wide, we might need to use multiple channels for communication, which is different from what Wi-Fi does. The other key difference between white spaces and Wi-Fi is that there is spatial variation in spectrum availability. In Wi-Fi, if you have your laptop or your phone, it can talk to your access point on any channel. Certain channels might not be as good as others, but you can operate on any channel. If I configure my router on channel 6, my client can definitely find it. Over white spaces, certain channels are blocked. The laptop, for example, cannot operate on channel 4 because it's in range of the TV tower. So if I set up my base station to operate on channel 4, I will never be able to connect to that laptop, right? So this is another problem that needs to be addressed. And the third problem is that of temporal variation. That is, this is where wireless mics come in. Suppose you have a base station and a client. Both of them are operating on channels 2 and 3. At a certain amount of time, someone switches on a mic. Suppose I'm giving a talk here. I switched on a mic. I'm operating on channel 2. This channel is unusable. So what this means is, at this point, this channel will be unusable. The system needs to reconfigure and operate on another part of the spectrum. This can arise because a mic comes up, because a client is mobile. I might be mobile. I enter a range where a certain channel cannot be used. So that's where this problem can come up. So to solve this problem, we have been looking at this problem. We have been looking at the use of cognitive radios. So cognitive is a very overloaded term. So Victor was at the back. I wanted to introduce Victor. Victor is the manager of the group. So Victor has been involved in this project right from the beginning. Yeah. 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 No, thanks for coming. Yeah. So to solve this, so in order to form this network where the spectrum has these 3 fundamental properties which are different, we came up with this idea of using cognitive or smart radios. So the idea is, as opposed to existing radios, here your laptop and your phone, they will determine which parts of the spectrum are available at each device. So my laptop, my phone, everyone would scan, figure out what parts of the spectrum are available, determine which part of that is commonly available at both the communicating nodes, both the devices that want to communicate, and use that spectrum for communication. So at Microsoft Research, we have been looking at the networking challenge, not really building the device as much, but once you've built the device, how do you communicate? So how should nodes connect? How do they discover one another? Which spectrum band should they operate in? What's the center frequency? What's the channel width? How long should you occupy a channel? Once you start using a channel, how long can you be in that channel? Which protocols should we use? And then prove the optimality of that. We showed that you cannot do any better than that. And this project, as you can imagine, as I said, since we've been working since 2005, it's gone through several versions where we solved different sets of problems, published different papers. Those are the ones in black. And they're still going on, and we've had significant impact on policy and so on. So in version 1, what we did was we looked at forming a mesh network. If you were to form a mesh network, how would you go about doing it? Most of this work was in simulations. In the second version, we looked at forming an infrastructure-based network. That is, you placed one node, one access point. We built a 6-device network on one floor of the building. We placed a node, had 5 nodes connect to it, looked at what the challenges were. How would you build the most efficient network? This was a small prototype. In version 3, we took our lessons from here and decided to go out in the wild, build the world's first Whitespace network. So in our campus, which is 1 square mile, we deployed multiple base stations, and I'll talk about that scenario. And in version 4 is what the rest of most of today's talk will be on, is stretching this to the limit. How can we be more optimal? How can we coexist with wireless microphones? So as I said, I'll just talk about these two, the first one very briefly, and then get into version 4. So in version 3, this is the first Whitespace network that we built. These are just some of the details. In fact, if you would have come during the day, I could have shown you the demo. The reason during the day is because this is running on our shuttles, the campus shuttles that run within Microsoft. So this is the Microsoft campus, most of it. And this is 1 mile by 1 mile. There are more than 70 buildings. And there are these campus shuttles that take people from one building to another. This is for meetings. And there are like more than 200 shuttles that operate within Microsoft. And right now, there is no way to connect to the corporate network from these shuttles. In a research project in a group, we did try to use Wi-Fi to connect. So just deployed multiple Wi-Fi access points on different buildings. On every building, we placed 4 different antennas. But even then, we found that we had huge number of these dead spots where we couldn't provide coverage. Over the white spaces, we tried to see if we can leverage white spaces to solve that problem. So for that, we were among the first to obtain an FCC experimental license to send and receive over the spectrum. And these are some of the pictures. Since I cannot show you the real demo right now, these are some of the pictures. That's one of the antennas we put on one of the buildings. There are 2 more. And the antennas on the buildings are essentially connected to an Ethernet backhaul. At the back of a shuttle, this is one of the shuttles, we have an antenna. This is a huge antenna. The reason it's huge is it's for experimental purposes. You can ideally build it in much smaller form factor. This antenna talks to the tower, and we have another cable that goes from behind the shuttle attached to the hitch next to the driver. This is the Whitespace device. This is connected to a Windows 7 laptop, which serves as an access point inside the shuttle. So people inside the shuttle can connect via Wi-Fi to the Windows 7 laptop. The packets are then sent over the white spaces, and this is how people are connected. So there are many challenges that we had to address in order to get there. One of them is designing the hardware itself. We used our hardware. We've also used other people's hardware, like those inside the shuttles. So this is just one sample hardware. So this is using off-the-shelf components, we built a device that could send and receive packets over the white spaces. Just to give you some, this is just one slide. We have an entire paper on this. But so this is how it works. We have a Windows PC, which has a Wi-Fi chipset. We modified the driver to change its channel width to 5, 10, 20, 40 megahertz. This is to use multiple TV channels if they are available. To this, what we did was we attached a software-defined radio, which takes the raw time samples, pushes it. We do the FFT here. We detect whether there's a TV or mic on that wireless mic on that channel. It goes to a connection manager, which then configures a Whitespace radio, which is essentially a front end attached to the Wi-Fi card to operate on a certain TV channel. And this is what it looks like, one of the devices. That's another device. There are a few more form factors that we've tried. And that's the huge antenna attached to it. So the other thing we did was we built our own version of a Whitespace database. So this is on this website, whitespaces.msresearch.us. You can go on that right now. You can put in any address here, click on Find Address, and then click on Show Nearby Incumbents. It will tell you all the TV channels that are available, all the white spaces that are available. We also have APIs that allow you to introduce a mic in the database. So the way it works is every Whitespace device in our system right now, it constantly keeps polling the database to see which channels are available. And one way, so when we built our campus network, the Microsoft network is a hotbed for wireless mics. Lots of them are in use. So we gave this API to the mic people here. They could introduce, if they faced interference at all, they could introduce their mic in our database using a command line API. During the break, we could give you a demo of that as well. And the way this database works is it takes as input the TV and mic data from the FCC, whatever is registered, takes the location as input, which is the address, and takes the terrain data from NASA. Then we run it through our own complicated, more complex propagation model, and the output is essentially at that location, what are the white spaces that can be used by the Whitespace device. Yeah?
So in your database, you have entered local use of microphones on the Microsoft campus, so those frequencies are permanently off?
No. If we ever did that, we would be blocking out all the TV channels here, because there's a huge number of wireless mics on campus.
Yeah.
In this building itself, we have 38 wireless microphones.
Yeah.
So this is only when you are either using the mic. So right now, we had asked the people to introduce the mic in our system only if they face interference. And we'll show you what interference sounds like.
This is a dynamically updated
Yeah.
database, okay.
This is a dynamic. I could update it right now, and you'd see a channel that is wrong.
Okay, thanks.
So we verified that our database gives accurate results. We had an intern. This was not George. This was another person with George, Rohan Murthy. He was from Harvard. He was super passionate, just like George is. And he decided to show us that the model that we were building was actually valid. So he drove more than 1,000 miles over a few days. And he would stop every 6 miles, step out with his gear, measure what the signal looks like. And this is data over 57 points. As you can see, this is going all the way to the Olympics and the other way. He would just drive in the middle of nowhere, got pulled over by the cops twice. Yeah, it is scary. Some guy coming out with all the equipment in the middle of a forest. It's like, what are you doing here? But in the end, what we used these measurements to show was over here. So what this shows is the accuracy of the model. How many white spaces do we lose? And this is what the free space propagation model would give us. This is where we are. And to the left is better. And what we saw was that, well, our database is much better than what the FCC mandated rules say. And we fed these back to the FCC, and they're looking at it. Another problem we had was where do we place the base station? So what we've done is, this is one of the buildings. This is building 112. This is where 99 is now. At that time, it was all like dug here, but right now there's a building here. This is our building. This is where we have one of the base stations. This is the entire route. We actually drove the shuttle. We were collecting the GPS reading every second, along with the signal strength. And here what we show is the actual range that you would get over the white spaces, right? So what you see is the green over here is UHF, the red is VHF. The x-axis is the distance from the base station, and the y-axis is the signal strength. As you can see, up to 700 meters, even beyond, you can get connected to a base station over the white spaces network. With Wi-Fi, we didn't cross more than 100 meters. So this could just lead to a separate kind of a network installation. So that's why the spectrum is so awesome. And our work over here, this is including the mic work, has gotten a lot of press. We had lots of people come in, take our interviews. Wi-Fi got a lot of press. And it has a lot of regulatory impact as well. We had the FCC chairman come here. The TRAI, Telecom Regulatory Authority of India, he came here to see our demos. He saw the mic demo that George will show in a bit, along with the shuttle demo, the campus shuttle demo and all that. So we've had a lot of impact. So now switching to version 4, I'm sure this is the part that you're most excited about. But before going here, I wanted to give you a little bit of introduction to why Whitespaces is so cool and some of the work we've been doing. So now, I don't know how many of you know, but the FCC passed the second ruling in, this was last year, September 23rd, 2010, where for wireless mics, it essentially reserved 2 TV channels. It said either side of channel 37, the first free channel is available for wireless mics. So there are 2 free channels. And the other thing is the people who are organizing bigger events can register their mics in the database 30 days in advance. Right? You need to know 30 days in advance what frequencies you're using. So while there are issues for the mic industry, it's also not super efficient for the Whitespace proponents, the people who were advocating for the use of Whitespaces for unlicensed communication. The reason is that each TV channel is 6 megahertz wide, while a wireless microphone is, as you'll see later in the demo, occupies only 200 kilohertz of the spectrum. And the FCC requires us to vacate an entire TV channel, 6 megahertz of spectrum, only if only 200 kilohertz of it is in active use by a wireless microphone. So that's not efficient. The other problem with this is wireless mics are not used everywhere. If I'm in my apartment, it's very likely that no one else is using that spectrum at that location. Why shouldn't I be using my spectrum at that time? And the third, most important point is, in big cities, we don't find many free channels. Over here, for example, this is a study that George did. In 39% of the cities that we looked at, we didn't have, if we took away the 2 channels, we didn't have any free channel for Whitespace communication. So what this means is, for Whitespaces to take off, you really need an application. You need people to build the hardware. They'll build the hardware if they see the economics behind it, if they see a use case. And if you're taking away 39% of the population right away, or even more, because these are the big cities, this technology won't even take off. They'll get killed before the first devices are out there. So that's why these are the 3 main reasons why we think it's inefficient. That is, first, just for 200 kilohertz, we are vacating the entire 6 megahertz of spectrum. Second, mics are not everywhere. Mics are only used in certain locations. And the third is there are not enough channels in big cities. On the other hand, it's also, yeah.
If I got this straight, then instead of 6 megahertz, if they were just to say, no, you don't have to abandon 6 megahertz, just abandon a 30th of that, you'd be okay, or do you have sideband issues? Or
yeah, we do have some sideband issues.
So all right, let's say a 10th then.
Yeah, yeah, okay, that would still be better.
That would be, yeah.
That'd still be better.
So what was the argument against that? Why not?
Why not? No, that would be a good first step. But the thing is that still doesn't solve the entire problem because of the sideband issue.
That would be
yeah. Because it would mostly solve the problem, but even then, even 1/10, you're still losing out the rest, right? Losing out on the rest, yeah. And the biggest problem is when I'm right next to the mic. The mic is here and I turn on my device. That's the worst case, right?
I'd argue it's a little bit of a misnomer to say, well, look, it's only 200K because it's, other issues.
Yeah. So that was the issue with the wireless industry. That's why we would like that problem to be resolved. From the perspective of a mic operator, so we talked to James Stoppo, who does a lot of mic placement. And he doesn't like the ruling because first, nearly all mics in different regions will have to be changed because you'd have to adjust your mics to operate only on the frequencies that are available there. And the second, the bigger one that he was concerned about was for his events, he says that I never know till the very last moment what channel I'll be using. That is, even every time he says at every event, I have to adjust my frequencies because of some noise that is happening at that location. And I don't know 30 days in advance. Even 1 day in advance would be difficult for me to know. So he wants existing schemes. He wants to have a dynamic placement. He knows the RF, what the RF looks like and wants to adjust his frequency assignment accordingly.
On your first point, though, isn't the rule that there are 2 channels reserved for microphones, but they can also use other channels as available?
So
they're not confined to those 2 channels.
As long as the mics, but they would have to abide by the Whitespace device ruling. So right now they can operate there, but that will all go away. Essentially, imagine if white spaces become as popular, we'll show you what the interference looks like. No one would like to operate their device on a TV channel on top of a white space device. I'll show you. It'll be the worst case. You'll really close your ears. It'll be like, hey, it's that bad. Yeah.
How much bandwidth are we talking about for a white space device communication?
So white space devices would communicate ideally audio, video, data communication. So if you have, 6 megahertz is one TV channel.
Right.
Right.
So how much does a typical TVBD bandwidth take up? I mean, microphones take 200K. How much does?
Oh, no. So phones are different, right? So if you look at LTE that is coming out, 4G, LTE, that's 5 megahertz of spectrum.
Okay.
Wi-Fi is 20 megahertz. So over here, even if you use 5 megahertz, well, you leave 1 megahertz for guard band. So you're using up the entire TV channel. Yeah. So given this, our goal was, well, it's short. We want to enable the white space devices to reuse the TV channel that is already in use by a mic. We want to do this without requiring any changes to existing mic deployments. We want to make your life simpler. We don't want existing mics to change while ensuring that white space devices can use that channel without interfering with the mic. So in the rest of this talk, first I will present how the RF interference from white space devices impacts the audio quality of a mic recording. So this is in a unique setup we did that. And then in the second part, George will talk about SEISMIC. This is a protocol we built and a system we built on top of it that allows this kind of communication to happen. We leveraged the studies, the measurements that we got from our study to build this protocol. So let me begin by giving you some background of what an analog microphone, wireless mic looks like. So it's essentially a one-way communication like this device that I have right now. This is the transmitter, and the receiver, essentially there are antennas here. The receiver is inside in a rack. All the mic receivers are sitting there. And the mic receivers themselves don't transmit. It's the transmitter. It's just one-way communication. There is a main carrier, this one, and there are two squelch tones around it. The main carrier carries the data. The squelch tones, essentially, whenever there is interference that is higher than the squelch tones, the audio is usually suppressed. Most mics suppress it. That is, all you'll hear is silence if you cannot see the squelch tones. And mostly the difference between the squelch tones and the main carrier is about 30 dB. Right? This is we found it standard across all mics. And in our study, we used 6 different mics. As you can see, the most popular ones, Shure and Sennheiser, are there. And these are all stuff that we got from the equipment manufacturers themselves. And this was a unique experimental setup. Before our study, most people, when you ask them about interference with mics, they would talk of RF interference. They would say, okay, in RF, how does my device interfere with the wireless microphone? Instead, what we decided to look at was the audible interference. And this is something we came up with this setup where in an anechoic chamber, we had a PC connected to the speakers. We had a wireless mic next to the speakers that was sending data to essentially there was a mic receiver here which sent the data back to the PC. And we computed the PESC value to look at the difference in the audio recording. Any audio questions? Well, Ivan will answer. Ivan really helped us with this setup to come up with this. And then what we did was we had a white space device with an RF attenuator. You see the RF attenuator there, the white space device. And we controlled the amount of interference that was input to the mic receiver. It went directly to the mic receiver. And in order to prevent any other RF interference to the mic receiver, we had it inside a Faraday cage. So all this setup was in the anechoic chamber. The initial plan was to take you all there, but there's already something going on. That is a very unique setup as well. And using this, we played a huge corpus of audio samples, and we would record play the original, do the recording, and then see the PESC value. How did that change?
Going back just a bit, you said audible. Can you define an audible in terms of, say, signal and noise or something of that sort?
So audible quality, right? So this is, so even you're the best to answer this, but PESC is what we went after because that was something we could compute using a computer program. I guess the better way would be to put it up and let people vote to see if they can hear any difference.
But
Oh,
that's
so
exactly
it
what
was
PESC is.
perceptual, yet I did people who said, can you
So
just...
pretty
yeah.
much the International Telecommunication Union in its recommendation P800 standardizes how to do a perceptual evaluation of sound quality, and it's called mean opinion score. Obviously you have you ask 100 people to grade the quality between 1 and 5. 5 is best, perfect, crystal clear. 1 is not usable, not audible at all, and then you average, and this is the mean opinion score. So it's a number between 1 and 5, which is what people think about the quality of the sound. Because this is kind of expensive and takes a lot of time, there is another recommendation from ITUT, which is called P864.2, which gives a computational proxy, a signal processing algorithm. You feed this program with the distorted sound and with the crystal clean sound reference, and it gives you a number between 1 and 5. If you do a user study with less than 30 participants, you better use the program, which will give you more reliable data. So at least we can do this completely automated. You don't have to call test subjects, etc., etc. And this is the so-called PESC algorithm, perceptual evaluation of sound quality. It's not perfect. It's actually very bad, but this is the best we have.
So the boundaries were perceptual. No one at this point, is it fair to say, said, let's translate this into some sort of numerical...
Yes.
Okay.
And pretty much we know that if there is a 0.1 PESC degradation, this is audible. And if this is 0.2 degradation in the quality, my semi-deaf grandmother should be able to say the difference. So if you keep the degradation below 0.05, this means that the quality is sufficient enough not to be audible except for somebody with extremely precise ears, like an audio engineer, for example.
Were the listeners trained or were they random people?
So the recommendation which ITUT gives, P800, does not specify the users at all. And PESC algorithm per se is actually a good signal processing algorithm, which ends up with a machine learning block, which is basically collects the samples from a couple of 100,000 people, their rankings, and tries to mimic their behavior. So non-trained people. Okay. At least they are not specified.
So that's why we used PESC. So that's why every time if Ivan is here, I'll deflect the question to him. So then we went about in this setup to quantify how does RF interference from a Whitespace device impact the audio recording. So here what we plot is the normalized score, that is, instead of going from 1 to 5, we picked the best value, that is the original recording compared with a wired mic recording. That had the best score. And we plotted the wireless mic recordings, just divided it with this value. So 1 would be perfect. So the higher you go, the perfect it is. So the first one is interference with varying time. So what we did was we introduced small packets, that is 16 microseconds long, which is smaller than the smallest Wi-Fi packet that the Wi-Fi protocol requires you to send. And we changed the spacing between that. So 16 microseconds packet every 500 milliseconds, every 1 second, and so on. And these are the audible pops that we can hear, even if the packet is just 16 microseconds long. This is a more scientific graph here, which says, as you change the spacing, this is in microseconds, how does this value change? Right? So even all the way to the end, we can hear the audible interference. That is, we hear these audible pops, even if they are very small packets sent more than a second after each other. The second test we did was interference in frequency. That is, around the wireless mic, we changed the amount of frequency that we suppress. That is, we do not use, so right now, most of the wireless technologies, the way they operate is they use contiguous spectrum. I'll use the entire 6 megahertz for communication. Here what we did was we came up with another technology which essentially notched subcarriers in the middle. So instead of the entire 6 megahertz, I'll use this spectrum and this spectrum and still carry out the data communication. And we were seeing how well that would perform. In fact, you'll see that in the demo. Then the next question was, okay, how much of the frequency do you need to suppress so that there is no audible interference? So we changed the amount of frequency suppression. That's what you see here. And this is, again, the normalized score. 1 is perfect. So as you can see, this is for one mic, the Sennheiser EW100. You needed up to 200 kilohertz of frequency to be suppressed. If you suppress 200 kilohertz for this particular value, you would hear no audible interference. Note that this is just 200 kilohertz of an entire 6 megahertz channel. You just suppress 200 kilohertz, you can use the remaining for data communication. And this is the amount of bandwidth that you need to suppress for different other mics that we studied. In one case, it went all the way more than 300, but for everyone else, it was below 250. 50 kilohertz. Yeah.
This is just a bad receiver.
Must be the BPU, I don't know which. So the next question was, so I showed you time, I showed you frequency. The third one is power. How does the amount of power, the power that you, the interference power, how does that impact the interference? So here, what we did was we changed the amount of power. So this should actually have been an animation where this went up in steps of 10. We changed the amount of power that we were interfering with at the mic. And what we found is that once the amount of interference power was above the squelch tones, at that time, the PESC value just went haywire. There was a huge amount of interference. Below the PESC value, you hardly heard any interference. And that's what these graphs show. That is, as we changed the amplitude, the green is for the squelch tone, the difference from the squelch tone. The red is the difference from the main carrier tone. This is 30 dB apart. Essentially, what this is saying is just 1 dB above the squelch tone is where we didn't find any, as long as you're just below the squelch tone is just visible, we did not have any interference in the audible recording. So to summarize, well, even short packets, very short packets, cause interference. So what that means is we cannot completely overlap with a wireless mic in the frequency domain. The second is the frequency, that is the number of frequencies you have to suppress depends on the distance to the mic receiver. Essentially, you want to keep it enough separated so that the squelch tones are visible. Similarly, the power, the interference, the amount of separation, the amount of suppression that you have should be such that the interference power doesn't suppress the squelch tones. That is, the squelch tones are visible at the mic receiver. So at this point, we'll switch to the demo. And George, you want to go through the demo? And then we can take the break. And after that, the next part of the talk will be given by George.
Can everybody hear me? OK. Hi, everybody. I'm George. So what we're going to do is show you our demo of actually avoiding interference with the microphone and still reusing the rest of the channel. And so what we've essentially done is taken some of these measurements where we understand what you need to do to reuse the channel without causing audible interference to a microphone, and essentially leverage them to still provide Whitespace device communication over the channel. So, I guess I'll just start off by starting the demo, then people can start to come up, ask questions, things like that, and we can have the break. So we have two devices here. These are the adapter Whitespace devices. So I'm just going to turn the Whitespace devices on first.
So Adaptrum is a startup in the Bay Area. They are building these devices.
You want to get the microphone ready?
Don't start transmitting just yet. So this is one mic, the Sennheiser mic.
So essentially what we're going to do is introduce the Whitespace devices into the channel without suppressing any frequency. They're essentially going to use the 6 megahertz, transmit constantly, and we want you to essentially hear what the audible interference caused by the Whitespace device transmissions actually is. Sure.
So on the spectrum analyzer here, what you're seeing is the mic in the RF domain. So this is what the mic transmission looks like, mic with this switch tones.
How does this handheld mic differ in its qualities from the lavalier mics that you're
It's similar.
using?
Yeah.
Similar.
For some of the measurement results we actually use mics like this. We use some handhelds and some like these battery pack.
So how do we know which one we're listening to when you've got your mic and the receiver?
So we
are
did
on?
for today's demo, these are on 600 megahertz, this is on 500 megahertz. So we know which one is ours.
Okay.
So you can hear this mic.
Barely.
Yeah.
I think this is.
Yeah. So
This will be really bad, so be prepared to unmute it as soon as you. So as soon as he starts the transmission, you'll see that the mic, I don't know if you can see this here, this will get swamped. I'll just put this to the back. This will get swamped with the Whitespace transmission. You'll
Yeah.
see the entire thing covered.
so okay. So essentially now the mic is close. So
Okay, that is muted. Yeah, so this is really bad, right? So
Right.
this is the kind of interference you'll see if you have a Whitespace device starting to transmit where you have a mic receiver.
right.
Right, it gets really bad. So then the next part of the demo, what George will do is he'll introduce the subcarrier suppression technique that we talked about. That is, can we just notch subcarriers around the mic, right? So as you'll see the transmission here and just suppressed around. So this is our transmission. We've notched it here. We have the remaining transmission here. You can see that they're actually transmitting video.
So I'll start the actual transmission here. So what we're doing is we're transmitting video from the one Whitespace device to the other Whitespace device. We are suppressing frequency around the microphone to not interfere with it while still maintaining our
So now
communication.
you don't hear that sound. The mic is still operational. Test, test. Right. And at the same time, the data communication between the Whitespace devices is still going on. So essentially, we are just suppressing less than 500 kilohertz of the spectrum here, and we can carry out the data communication, video communication. That's HD video. That's taking up a lot of bandwidth, but it's 5.5 megahertz. Yeah.
And that notch has been calculated by you, or it's been sensed and?
So this is what he'll talk about in the next part of the talk. Yeah,
Okay,
that's
thank
it. So yeah, so now we can take control.
Yeah.
If anyone wants to see the demo, come close and.
So break time. Kids in the water is in the back. If you guys want soda or Coke or something, there is a refrigerator on the end of the hallway right there. And feel free to come here. Down for filming. For how long will you get over there?
Let's do 15 minutes, and the restrooms are out the door and down the hall. You'll see a sign. There's refreshments.
Hi, everybody. My name is George Nychis. So, as Ranveer introduced me before, I'm a PhD student at Carnegie Mellon University. And I did a lot of this work while I was here as an intern under Ranveer and working with Ivan, et cetera. So what I'm going to do is present SEISMIC, Spectrum Efficient Interference-Free System for Mics. So what Ranveer presented was the study of RF interference on audio disruption for microphones. And so essentially what we showed was something great. Coexistence can actually happen on the same channel between Whitespace devices and wireless microphones. We can have no disruption on the mic audio and gain up to 97% of the channel around the mic. So essentially the results show that only a single condition need to be true, that the interference power needs to be below the squelch tones. If it is, no matter what, we're going to hear audio disruptions. Great, right? So all we need to do is know the mic center frequency and then suppress the amount of bandwidth that the mic needs, right? So essentially, some of the results that Ranveer showed is we have these 6 microphones, and this is how much uninterfered with frequency that each microphone needed, right? So center frequency, mic bandwidth, and we're home scot-free, right? Unfortunately, it's not that simple. So the amount of suppression that's actually required all depends. So unfortunately, Whitespace devices cannot suppress frequency perfectly. So the reason for this is as they try to suppress frequency in a band, there's some amount of power that is essentially rolled off into the band that they're trying to suppress in. So they essentially cannot suppressed perfectly, and power is essentially leaked into this area. And so, for example, here, what we did is we present the frequency and power that's the result of trying to suppress frequency from the Whitespace device that we used in the demo, the Adaptrum device. And so what we do is we keep the power constant from transmission and slowly try to suppress more frequency. Now, if you had perfect frequency suppression, what would happen is if you suppress something like 80 kilohertz here, it would be suppressed the entire way down, right? But it's not. Unfortunately, what happens is that power rolls off into the area at which you're trying to suppress. And so essentially, with perfect suppression, this would be a lot easier, but unfortunately, this is a fundamental problem with trying to suppress frequency with Whitespace devices. So the impact of this is that suppression is going to essentially need to vary. The stronger the Whitespace device is in terms of interference, the more suppression is going to need to happen. And essentially, the weaker the mic is at the mic receiver, you're also going to need more suppression. And I'll show this in terms of an illustration why this is. So first, let's take this example. So right here, what we have is we have our microphone, and we're suppressing a certain amount of frequency such that we are not interfering with the microphone. The power in the band is lower than the power of the squelch tones. Therefore, we're not going to have any audio disruption. But now, what happens if the microphone power is actually lower at the mic receiver, right? So what we would do is try to suppress this amount of frequency, but that would not work because of the power that's rolling off into the band. So it's not sufficient, and this is essentially changing based on the power of the microphone. And so what would actually need to happen is we would need to suppress more frequency to not interfere with the microphone. So clearly, the amount of suppression that we need is going to change based on the mic signal strength. But now to make the problem harder, let's take this scenario. So we have our microphone power. We're going to fix the microphone power. In this example, we're essentially showing that this amount of suppression is sufficient. But now, what if the power of the Whitespace device is actually higher? Here it was at roughly 40 dB. Here now we're getting closer to 50 dB. If the Whitespace transmission interference is higher, essentially it's no longer sufficient again. What we would need to do is suppress more frequency. So this is essentially two cases where I've shown where the mic signal power is going to matter in terms of the amount of frequency suppression needed, and so is the Whitespace device's transmission power. So to further show this, what we did is we evaluated how much suppression we needed when we essentially kept the microphone power fixed and we changed the interference power of the Whitespace device. And so here what we have is the amount of frequency suppression on the x-axis. And on the y-axis, we have our normalized PESC score. And so I have these sort of small gray lines which show for each Whitespace device interference power how much frequency suppression was needed. So for example, here, when the Whitespace device power was low, we essentially need only roughly a small amount of frequency, like 25 kilohertz. And the reason it's so small is because we're basically just below the squelch tones already. And so as we go on, and the interference power becomes greater, we need to suppress more frequency, 200 kilohertz, 275 kilohertz, almost up to 350 kilohertz. So what we're doing is we're showing that essentially the amount of suppression that is needed is going to vary. So this is a challenge, right? So it's extremely challenging because essentially the information that we want to know is at the microphone receiver. So if we have a wireless microphone, the wireless microphone's receiver, and a Whitespace device, there's two pieces of information that we want to know at the Whitespace device. The first one is the mic signal power at the mic receiver. And the second one is the Whitespace device's interference power at the mic receiver, right? So this is essentially going to matter in terms of how much frequency we need to suppress, right? All of this matters at the mic receiver. But unfortunately, the mic receiver is completely passive. The mic receiver transmits nothing, right? And so to make this harder, some things that have been used in the past is something like channel reciprocity. If I know someone's transmission power to me, I can roughly estimate my transmission power to them. But since this mic receiver does not transmit, we cannot estimate essentially our interference on the mic receiver. Likewise, we can sort of estimate based on the wireless mic, but that does not tell us what its power is at the mic receiver, right? So we essentially don't know either of these components, and this is what makes this problem extremely challenging. So we can only essentially do proper suppression if we know both components at the Whitespace device. If not, we would unfortunately leave the mic susceptible to audible interference, and we do not want to do that. So I'm going to present is an overview of the SEISMIC system. And so essentially, based on these challenges, what we're going to do is augment the mic receiver with what we call a mic protector. And essentially, what this mic protector allows us to do is monitor the key components that allows us to perform the suppression. So right now, we picture this as a standalone device that you could put onto a legacy mic system, but we envision this type of system to be built into future mic receivers. And so the mic protector is providing a couple key components. So it's enabling interference detection at the mic receiver. And what it's going to do, which I'll talk about, is notify Whitespace devices of impending disruptions to audio. So the key word there is impending. We never, ever want the audio disruption to occur, so it's going to allow us to adapt before it occurs. And so all of this is essentially going to leverage measurements that we did that Ranveer had presented with the very in-depth understanding of what exactly causes audible interference on microphones. So what I'm going to do here is present the mic protector design. So this here is the view of the mic protector. Think of it as. On the x-axis, you have frequency, and on the y-axis, you have amplitude of your signal. So this is sort of, I'm giving you the inside view of the mic protector. And so here we have some mic that is essentially protecting. So the mic protector implements three key components. The first one is interference detection. So essentially what we need to understand is what the level of interference is from the Whitespace device. And to basically measure this amount of interference, what we do is we introduce two very small, just 25 kilohertz bands on each side of the mic. And essentially by doing that, we can measure the amount of interference in these bands without having to try to measure it within the mic's operational band, which is difficult because once this mic becomes active, the power in there is going to essentially shift due to the FM modulation. The next thing it's going to do is provide interference protection. So I'm going to get into how exactly this happens. But what we knew from the mic interference measurements was any power that's below the squelch tones does not cause audible interference. So essentially what we're going to do is introduce a protection threshold below the squelch tones, and we're going to monitor them. Anytime the interference is below these squelch tones, we're OK. As the interference begins to approach it, then we have a problem, right? And so what we're going to do is monitor essentially the noise in relation to this protection threshold. And I'll talk about how we ensure that it never exceeds this threshold very soon. And then the final component of the mic protector is the notification of impending interference. And to do this, what we did is we introduced a simple technique called strobing, where essentially what we're going to do is introduce a signal in the control bands that are just outside the mic's band. And once a Whitespace device detects these signals, it knows that it's about to cause audio disruption to a mic. And so these three components are essentially what we build the SEISMIC protocol on top of. And I'll talk about how we can actually do this without ever interfering with the microphone soon. So just a brief overview of strobing. Strobing is just one technique that we came up with to essentially allow notifications to a Whitespace device without adding a lot of complexity to them. So essentially what it does is a strobe conveys that there's impending interference on a microphone. And what we're doing here is we're essentially introducing and removing power in these control bands. And so if you look at it, you could see it as it's similar to something like a Morse code, right? We're essentially like strobing a signal. And it's also similar to on-off keying for those of you who are more wireless oriented. And so what we do is we quickly introduce and remove power into these bands. And from this, we essentially allow notifications to a Whitespace device. And so you can sort of think of it as like carrier sense plus plus. All the Whitespace device is doing is looking for power of certain of patterns that match these strobe patterns. Okay, so what's extremely important is the SEISMIC protocol, right? It's how we can actually determine how much to suppress without ever interfering with the mic's audio transmission. So what the mic protector is doing is essentially monitoring the interference and strobes a Whitespace device if there's impending audio disruption. So again, impending is the key word here. So how do we do this? How do we actually leverage the spectrum around it without ever interfering? So what the Whitespace device does is it sends short probes with increasing transmission power. And then anytime the Whitespace device says, hey, you're getting close to my protection threshold, it suppresses frequency and then tries again. And I'll give an illustration of how it does this. But essentially what we're doing here is we're exploiting the FM capture effect, where any interference below the squelch tones is not going to create audible interference. So we're going to use this as sort of like a way to signal with the mic system. Sure.
Is that handheld still turned up? There's a buzz coming out of the speaker.
This is on.
On the receiver side of it.
Okay, let me try this here.
That's worse.
Disconnected from the laptop.
Oh. Trying to unplug stuff until it goes away.
That's better.
No, it should be off.
Thank you.
Everybody good? Okay. So let me give you a view of what happens from the view of the mic protector. Then I'll give you a view of what happens from the view of a Whitespace device. So again, here we have this view. And what's going to happen here is a Whitespace device is essentially going to start probing the channel. It's going to send just a little bit of power in a probe packet. And then it's going to listen. It's going to say, OK, am I going to cause impending audio disruption to any microphones? It's going to listen for strobes. If it doesn't, it keeps increasing its transmission power. And so this is going to happen when a Whitespace device first enters a channel. It doesn't know the placement of any microphones. It doesn't know their powers, anything like that. At this point, it's trying to converge to proper frequency usage of the channel. So slowly, it's going to increase its transmission power until it hits the protection threshold. At this point, the SEISMIC protocol is really going to kick in, and essentially the Whitespace device is going to adapt to the microphone being in the frequency. So to do this, at this point, what the mic protector realizes is, hey, if you transmit any louder, you're going to cause audio disruption to the mic system. So what it does is it notifies the Whitespace device of this by using the strobe signal. So what happens with the view of the Whitespace device, and how does it actually converge? So we have here is time, and we have essentially packets from a Whitespace device and the mic protector. And so blue packets are going to be these probe packets, where it's slowly increasing its power. And then the strobe packets are going to be these responses from the mic protector. So the Whitespace device enters the channel. It doesn't know where any microphones are. It sends a probe packet at a minimal transmission power. Here's nothing. It increases its power slightly and probes again. At this point, the mic protector essentially strobes the Whitespace device and notifies of impending interference. It says, if you transmit any higher, you're going to interfere with me, right? So what the Whitespace device does is instead of, saying, I'm not going to use this channel, it's going to say, hey, what if I suppress 50 kilohertz? Is that good enough? If it's not, essentially the mic protector will strobe back and say, nope, still not good, right? And essentially the Whitespace device is going to react and say, how about 100 kilohertz? And at this point, this protocol continues. If 100 kilohertz was OK at that transmission power, it slowly begins to ramp up again, right? And by essentially the protocol between the Whitespace device and the mic protector, back and forth in this way, what the Whitespace device essentially does is it converges to optimal frequency usage in the channel at a maximum transmission power. So we've essentially converged to coexistence of the Whitespace device with the microphone in the channel without ever causing audio disruption.
What kind of a safety net do you have there?
Right. So essentially we have this protection threshold, right, which is the point at which it's going to notify. So we did a pretty in-depth study of where this threshold needs to be. The threshold essentially needs to account for several factors. One is the fact that the mic's signal strength is changing over time, right? And so essentially what we want to do is protect that at any point in between one of this, the value can essentially change. And from that, we want to make sure that that protection threshold allows this fluctuation, right? And so in implementation, we end up using a 10 dB separation between the squelch tones and the protection threshold. And we've done a bunch of evaluation to show that even if you separate it more, the amount of loss that you get from frequency reusage is not significantly high, right? Mm-hmm.
What's the real elapsed time to get to this?
So in our implementation, we end up using software-defined radio to do this. We can essentially converge on the order of hundreds of microseconds. If you were to actually implement this in something that can do this process faster in terms of detection of strobes, the time they take to transmit, it could go lower. So that's the nice thing about being able to enter a channel and converge without having to spend a lot of time seeing if it's going to work out.
So from a user perspective, it's essentially instantaneous.
To us. Right.
And you've been talking so far about one microphone and one Whitespace device. Are you going to talk about multiple?
So I'm not going to talk in detail about multiple, but this does work for multiple microphones, and we have a formalization in our paper that shows that this essentially will work for n number of microphones in a channel. And if you think about how this works, essentially, what it does is it slowly ramps up its transmission power. 50 kilohertz might work for one mic in this part of the spectrum, then maybe it needs 100 here. As it starts to ramp up more, then this one's going to yell at it, and it needs to suppress more in this area. And so eventually what you do is you converge to multiple notches in the spectrum.
And what about multiple Whitespace devices? Did you say that the notch is cumulative as you add more whites? The bottom of the notch is cumulative as
Right.
Whitespace devices?
Correct. So the problem with this would be that, let's say that multiple Whitespace devices ramped up at the same time, right? And so this is something that one of our other collaborators, Thomas, worked on, which was a formalization which shows that if there are multiple Whitespace devices that are essentially ramping up in the spectrum at one time, this accumulation will still not exceed our protection threshold. So essentially, we can allow multiple to ramp up without audio disruption.
Can I ask a more basic question?
Sure.
If you have one device where it's the bottom of the notch is, what is it, minus 30, minus whatever. If you have two devices, is the bottom of the notch higher in absolute energy present?
So that's additive there. So it will be higher. We don't expect it to, let's say, like all add up excessively, because no one Whitespace device is typically going to be transmitting at the same time as another Whitespace device. Typically, these do carrier sense, right? Right. So
if I'm in an auditorium with 500 people and 499 of these devices, or 5,000 people and 4,999 of these devices,
right.
is the bottom of the trough going to be higher than my microphones?
No.
By definition?
No. So the reason
The simple presence of those things?
Right, so the reason for this is this convergence period where, let's say that whenever they converge, if they're transmitting at the same time, that additive will still be what the mic protector strobes back against, right? And so it's going to be protecting about the additive interference in there. Thomas is definitely the best person to ask about this, but we have a nice formalization in our paper which shows that even if they did all try to ramp up, we still will not exceed that threshold.
They're additive, right? And every time, so two of them at the same power, you're adding 3 dB. Right?
Okay.
3 dB is down.
In the best case.
That's the best case, right? So and you're already taking that as a reference point. If they ramp up further, the relative increase is the same, right? It's still whatever it is plus 3 dB. Individual's power plus 3 dB. So you can treat it as the same device, one device, right?
Yeah, but if I've got 5,000 of these things there,
Well, but during
It's turning on at the same time.
yeah, that's what I mean. So on the analog, the microphone, those would be like continuous time transmission FM. They're always transmitting.
Microphones.
The white space is not like a continuous
Yeah,
transmission.
it's
kind of
intermittent.
bursty, packety.
Right.
So even though you have 5,000 white space devices, they're not all on at the same
All
time.
at
The way the microphones are on at the same time.
These
Right.
are sending on an FM carrier, that's OFDM based, right? So only when I have to send a packet, I send it. And the other thing with these devices is if it's Wi-Fi based, if all of us are in the auditorium, only one will send at a time. Everyone else is going to back off. They don't transmit it because the carrier sends. I sense the medium, if it is free, I send. If there are 5,000 people, well, even then, if all are in sensing range of each other, only one will send. And since white space devices are so long range, you don't expect all of them to be active at the same time.
so if these devices are telephones, or cell phones, only one person can talk at a time?
Cell phones is different. They follow a different protocol. This is for unlicensed spectrum or ISM bands. This is something that is specified. You cannot just go and hog the medium.
Okay, so at the break, I asked what kind of devices these white spectrum feature things that are going to be developed are going to be. And we came up with cell phones and computers.
No,
But-
cell phones as in
The data
smartphones.
channel,
Data channel.
not the telephone channel.
For browsing.
Part of the data.
Just like you browse over Wi-Fi.
Smartphone sending data rather than voice.
You could use it for an audio channel, but even then you have small packets and you're not always sending, just like you do Skype or something else over your laptop. It's the same protocol. It's using Wi-Fi, but it is not always sending. Even if I'm the only user, the only laptop connected to the access point, it's not always transmitting. It sends a
That I
packet,
understand,
waits for a while, sends another.
but if I have 5,000 of them who are...
Skype won't work, right? So that time, such kind of audio communication won't work.
They're going to clog up each other, just
Yeah.
like if you have too many Wi-Fi devices in
Yeah.
a given area.
Oh, okay.
Question?
I take it the strobing is carrying the center channel information, so you're not actually trying to sense where the center channel is.
Right. The strobing is actually cute in that sense. It's something I wanted to bring up, but forgot to mention real quick. But the nice thing about these control bands is they are on both sides of the microphone. And once you detect these two strobe signals, you know the mic center frequency as the median point between these signals. And you know the mic's bandwidth essentially by the distance between these signals. So it's basically learned from the location of the strobe signals.
White space device is finding this frequency of the strobe as well, so you don't necessarily even have to go by 50 kilohertz increments. You can start at
Yeah, you could start at something bigger to converge more quickly.
based on where the strobe frequency.
Right, you could do that.
Yeah, I live in an area where there's probably like a dozen different networks, and they're all on Wi-Fi, and you can see them all when you're trying to connect to your own network, and they're all on the same frequency pretty much, and they're not conflicting with one another. But you said that you can only use one of these at a time. Why not somehow negotiate like Wi-Fi does?
You mean one mic protector, or maybe I'm not understanding the question?
Well, you said something about only one white space device transmitting at a time.
Oh, so what we're saying is, though, even though there are n number of networks that you see there, at a given point in time, what happens is that a device carrier senses for the channel. It says, okay, there's n number of us, but only one of us can actually successfully transmit at a time because we're using the shared medium. So what happens is I transmit, then you transmit, then I transmit, then you transmit. So even though there's two of us, actually at one given time, only one of us is transmitting. Yeah, and so we essentially alternate using the medium. These are packets, right?
Yeah, continuous.
Correct. And so the downside is if there's 1,000, then you have to alternate between all of you. So that's why when there's a lot of networks, it's worse because you have to share with that number of networks. Okay, fast forward here again. Okay, so just a quick summary of the SEISMIC design. So what we did is we introduced a mic protector, which monitored the key components to understand how much frequency we need to suppress. So again, we pictured this as a standalone device, but this could definitely be built into future mic receivers. So the Whitespace device and the mic protector essentially engage in the SEISMIC protocol. And what we showed is that by doing this, we essentially ramp up to an optimal suppression and maximum transmission power without ever creating audible interference on the microphone. And so I guess we've talked about this a couple of times now, but you can see the white paper that we have in the upcoming Conex 2011 conference, which shows that we can actually perform this with multiple microphones without ever creating audible interference for them. Question?
What happens when there are so many microphones in use that there's no spectrum left?
So if there's a lot of microphones in a channel, I mean, this is a decision that the Whitespace device will essentially need to make. It'll say, you know, using this channel at this point is not worth it to me, maybe. You know, maybe if there's 25, 50 microphones, it might say this channel is simply too busy. And the amount of benefit I'm getting from that channel is not significant enough, right?
So that means that Whitespace device will not function. It'll send a message saying we cannot operate in this space at this time.
In that channel. It could use a different channel instead. Right, so some of the work that Ranveer did on networking over the white spaces looks at, you know, we have all these spectrum fragments, and essentially they came up with a metric that said, with all these fragments, let's pick fragments that are simply, you know, the best to use in terms of bandwidth. So for this, you might decide, because there's so many microphones, we're not going to use a specific fragment of the spectrum.
39% of the urban areas that have all wireless microphones.
Yeah, so we'll show some results with many mic scenarios. The nice thing is that mics do exhibit FM. So in some scenarios where we evaluated, we showed that you didn't even need to suppress anything. And the reason for that is your interference is below that FM capture level. So there is that nice property of FM microphones. So what we did is we evaluated SEISMIC. So we built a full prototype of the mic protector and a SEISMIC-enabled Whitespace device. And we evaluated real-world scenarios. So for example, a mobile microphone 20 to 30 feet of the mic receiver, like something within this room. And that's like somebody taking the microphone, walking around. Maybe we're at a concert, we're swinging it around, we're excited, right? And then we also evaluated it under a mobile low-power microphone scenario. So this is something like the distance between the mic and the mic receiver is great, and the microphone is operating at a relatively low power, which is challenging, because we need to make sure that we never interfere with the microphone in that scenario. So the key thing here is that what we're really evaluating is SEISMIC must properly adapt. So mic powers fluctuate. So I just gave 3 simple scenarios here that we measured. So the first one is a stable microphone. And on the x-axis here we have time. On the y-axis we have the amplitude of the squelch tones. It could also be something like the amplitude of the mic signal. But when the mic is stable, let's say if it's on like a podium, essentially that signal is stable. But now what happens in the second plot here when human interference comes in? It's stable, but now I'm sort of walking around, right? And so by doing that, I'm essentially fluctuating the microphone signal. And on the third one here, I showed having the microphone in my hand and essentially walking around, picking it up to my mouth, dropping it down to my side, et cetera, turning my body. And by doing that, that mic signal can fluctuate a lot relatively quickly, right? And so essentially, SEISMIC must adapt and never interfere with any of these scenarios.
Have you tried this, say, under circumstances maybe akin to, say, the Fifth Avenue Theater or the Paramount, where they have, you know, quite a number of people with mics who are actually moving?
Right.
You know what I'm talking about.
Yeah.
Real world.
Right.
How did it turn out?
Yeah, so we did not get to evaluate under these scenarios yet. We've been actually in talk with James Stuffo about actually taking our system and seeing how it works at the Latin Grammys. And he invited us to some other events where essentially they have a lot of microphones and they want us to see how our system performs in these scenarios. Yeah.
Doing what?
Yeah, right. And so essentially, we want to evaluate this under these scenarios. We have not gotten the opportunity yet. So what we've done is we evaluated it under single mic scenarios, multiple relatively smaller scenarios, right? So.
And when you do that, you're going to have to put one of these interference detectors on every microphone.
So what we do is we require one for an area. Like, so let's say here what we have is we have a rack inside which has multiple mic receivers for the mics in here. Essentially, what we only require is one mic protector for that area. Because essentially all it needs to do is accurately estimate the interference of the Whitespace device and the mic signal. And by putting it near that rack, it essentially can do that for all of the receivers.
As long as it knows all the frequencies of all the receivers.
Right. It needs to know the frequencies of the receivers to essentially protect. Right.
So it's not necessarily built into every receiver.
It does not need to be, right? So what we've done is we've built a standalone prototype that could protect something like a rack. In the future, it could be built into every mic receiver, and therefore, you wouldn't need one to.
So you would not need to buy all new receivers when this goes into effect. You could get
Exactly, right. This is a key thing that we wanted to essentially enable. We don't want to change legacy mic receivers in any way. We want to allow essentially the mic industry to operate, and we want to provide protection for them while we're using the channel.
Okay.
Right.
What's that going to cost? I mean, so this might.
Yeah, I mean,
$50 or 500?
it's a good question, right? It's nothing that we've really been able to evaluate so far. In terms of complexity of the device, the complexity is not high, right? Like, for example, we developed the strobing to do basic power generation, things like that. And essentially, all it needs to do is monitor interference power in an area, right?
It's already monitoring interference, most of them, right, to figure out the best channel it should be operating. The transmitter is a very cheap transmitter. Strobing is using on-off key, which is like very simple to implement. It's not doing anything, no FDM, nothing. So that way it's relatively cheap because it's already doing the interference detection. All it needs to do is
only once. The mic receiver is only doing it when you tell
No,
it
but the
to.
hardware, it won't cost more to do
Right.
it multiple times as opposed to one. The hardware is already there. Just the
It
transmitter
depends-
needs to be added.
It depends how many you want to manufacture. If you manufacture 100,000, you go to VLSI chips, it will cost $5.
So can you predict about how long it'll be before you actually test it out in these real-world environments?
Yeah, so I mean, we were invited in November to evaluate this at the Latin Grammys. So that's something that we definitely want to work with James on doing and evaluating there.
Next month.
Yeah, so it's within a month from now. Something that we want to do, and he does various events, and so it would be great to evaluate this under these scenarios.
So the reason we are not giving a time frame is we are swamped with different things, and we really need to. This is something that James wants to take forward to, so we are working with him to do so. If there's an event in Seattle or Pittsburgh, makes it easier because if it's in Seattle, I can do it here. George can do it if it's in Pittsburgh.
Right.
So we are looking forward to the right opportunity. This year's company meeting, the Microsoft company meeting, would have been a good opportunity. He comes, does it for us there, but I wasn't in town at that time. So. But we'll do it soon. That's something which is higher on our agenda.
Do you have contacts at, say, the Fifth Avenue or the Paramount or Benaroya? Would you want some?
Yeah, if you're here, yeah.
Okay.
Yeah, definitely.
We can do that.
If we have friends there, because we don't want it to be a public event. It's just research.
Right.
Yeah.
Well, knowing people there, you could get in on an off day and fool around with
Yeah,
it.
yeah, that would be nice. Just to
Okay.
do some testing.
Okay.
Yeah.
We can make that happen.
I have a question
Sure.
about the microphones. What is the property of the microphones that determines the amount of frequency the band has to be suppressed?
Okay, so essentially what the operational band of the microphone is.
No,
So
No, but I mean, what is it about, like you said, different microphones need to have for different microphones to prevent interference, you have to suppress different bands of bandwidths of frequency. Okay, what
Right.
is it about each microphone that determines? Is it something about the transducer, or is it something about an audio property of the microphone? What is it that determines that?
So I'm not a mic expert, but my intuition/knowledge would tell me that it would be something like the frequency range of the microphone. So essentially what you're doing is you're doing FM modulation, where based on the frequency input, you're shifting the frequency of your carrier. So it could be something like
chart, and then for each one of them, there was a different rating. And the question is, what is it about, have you looked at what the properties are of the different microphones and what they have in common, and what factors about the microphones result in that?
Right.
So the guess is, I think it's the receiver hardware.
It would be the modulation index.
Yeah.
And the receiver sensitivity on each one of these, the RF components are different. So each one has a different RF receiver sensitivity. Someone can operate at SNR, depends on the SNR at which they can operate. So that's the more bandwidth you suppress, the less noise we cause. And each receiver, I think each one has their own RF component, and whatever sensitivity that they have determines the amount of bandwidth that they have to maintain.
Yeah, but the microphone itself,
She was wondering
how
what
does that
causes the
relate
difference.
to, how would that relate, that's different from RF, because the microphone is just a transducer.
I don't think it's the microphone itself, it's the wireless mic system's receiver.
Oh, okay.
Yeah.
Okay.
Receiver, that's what's going to pick up the interference.
Okay, okay.
In the paper that was recommended that we read before this, which was Whitespace's devices performing in a Wi-Fi, like a Wi-Fi, I don't remember the title of it, but there was a cute trick in there that where when the Whitespace devices decide on an initial channel that they're going to transmit, they at that time create a secondary channel to jump to should a wireless might click on in the primary. Is that still operative in this?
So that is a separate paper. That wasn't about interference. That was about if I have a link gets congested or blocked, how do I recover the link? So this concept of the backup channel is being considered as part of the standard, the Wi-Fi standard, the 802.11af standard. So yeah, but we're not talking about that in this paper. But yeah, that is.
But that would be incorporated into this
ideally,
if it got adopted.
If it got in.
That seemed like a good idea.
If, you may be going to discuss this yet, but what happens if the mic gets turned on? You're going to have a moment time. How often does the Whitespace device look for the strobe, et cetera?
Right. That's a very good question. So essentially, I'm not going to talk about it in here, so I'll talk about it right now. We have it in the paper, but essentially, when a microphone turns on in a spectrum, this is an immediate cause for concern, right? Because all the Whitespace devices have converged to some point that is ignoring the presence of this microphone. So when a microphone first enters a channel, what the mic protector does is it sends a special strobe that essentially says, hey, I'm a new mic in the channel. And because of that, that needs to essentially kick the Whitespace devices back into convergence mode. And so whenever a new mic enters, all the Whitespace devices converge again. And that convergence accounts for that microphone. So we consider that like a special event, a microphone entering. When a microphone leaves, so what we do in terms of the protocol is periodically we reprobe for frequency. We essentially say, okay, can we, add a little bit of frequency back? It'll strobe at us if we cannot. If so, then we keep adding a little bit more. And essentially, if a mic leaves, over time, we will essentially regain that spectrum.
Is that audible? Say not with one mic, but say several mics come in and go out.
So mics coming in, it will not be audible. Mics going out will also not be audible. And the reason is that once we've converged to this point, we've essentially stepped up to using that frequency. If we want to use that frequency again, we step down and try to essentially put a piece of that spectrum back in. Because we've already verified that that previous step works, right? That's how we got there, right? Things will fluctuate over time, but if it does, we essentially have this protection threshold, which will basically yell at us if we need to back off more.
It will work as long as the incoming microphone isn't off stage back where it's really low and level. Your mic protector is able to even tell that it's there trying to come on.
So in terms of that, the mic protector needs to essentially know that the mic is turning on, right? So the mic protector is near the mic receiver. If your mic receiver can't hear your mic, then that's a separate problem, right? But essentially, that mic receiver will know that that microphone is turning on.
So it'll start strobing. I mean, as soon as or it'll start sending out its pulse as soon as the channel kicks on.
As soon as it detects the carrier wave.
Right.
as long as the Whitespace device isn't loud enough that it's swamping the carrier wave.
Yeah. And another question?
What about the case where you have a stereo pair of microphones that is now being dynamically changed when another mic comes in or comes out? Because you're rejigging the system of mics. If you've got a left and right pair of mics, I don't know if you actually use this in practice. Someone in the industry can tell me if it's not done in practice, then forget the question.
Actually, I remember a case at the Fifth Avenue Theater where there were three pairs of 451s like this across the stage where that was dynamic. Well, I don't
Those are
know dynamic, but it
wireless.
was.
Those are wired.
Wireless?
Those weren't
I'm
wired.
sorry, you're right.
Yeah.
You're right.
I
That's what I
would
just
think
said.
every one of them is an individual microphone, so multiple microphones.
It'd be really rare to do
So it's
stereo.
rare case, you forget it doesn't matter. Because otherwise now you have
Partly
you
for
have a
the
level-
reasons you're mentioning.
You have a level of phase difference in channel to channel. Now your image is wandering around.
Yeah.
Yeah, but that's in the
not
audio
done in
spectrum, that's not in the RF
Yeah,
spectrum.
that doesn't relate to this.
Okay, forget it.
Isn't it important to differentiate between the receiver location and the antenna location?
Receiver and antenna
Because the
location.
antennas are not necessarily located at the receivers.
Right, right. Yeah, that's actually an interesting point. So how we've essentially evaluated these receivers are the antennas are essentially connected to.
Well, they're going to be connected, but they're not going to be in the
Right.
specific-
So the way that you can handle that, which is what we've done with some of these systems, is essentially the mic protector is basically bridged into the system via that same input, right? And so from that, you have the same view as the antenna rather than the
They
mic
don't
protector.
have their own antennas, they're using the existing
Right.
system.
Right, right.
Okay. Except in a case, that assumes only one set of antennas for a pile of receivers. If you have individual antennas on receivers,
Right. So in that case,
they're different frequency bands.
in that case,
And they're significantly different locations of antennas. I mean, usually when you have a couple of stacks, you're going to put them in racks next to each other, so you're virtually in the same space.
Right.
yeah. So maybe in that case, you need an additional mic protector if they're significantly separated. But I mean, it's really good to hear sort of what your use cases are because we don't use these systems as much as you do, obviously. So this is actually really insightful.
But different frequency
I'm
bands.
curious what kind of data is being transmitted on this white space. Are you able to take multi-channel audio and send it out?
So essentially, what's over these white space devices is some data transmission, right? I mean, it can be essentially what your laptops do today in terms of, either carrying video, carrying Skype calls, basically any sort of data communication. So
It rained a week or so ago. They talked about Ethernet proprietary systems for transmitting broadband audio among devices. Is that the quality of transmission you're going to be able to do with the system?
I'm not too familiar with that.
One of the thing, most Ethernet-based audio transports, the main thing is they can't tolerate drops. In other words, they can't tolerate other devices trying to talk on the same network.
So it can't
And
come back.
well, they can do that a little bit, but they can't do a lot of it. And so this is a public unlicensed where anybody else might try to use the same channel, so to say. And so I think the network traffic would become too congested to allow that to happen efficiently. But if you're able to isolate and say, this is my network channel I'm doing, then that you would be able to.
There were multiple attempts to do high priority packages for audio and video, and so far didn't work. Otherwise, yes, in the perfect case, if this is the white space spectrum, your microphone is a white space device, and everybody has the same protocol, everything is nice and clean, unless 500 people take out their cell phones and try to browse internet, it gets congested, you lose sound. So for now, there is no way to say, okay, I'm an audio device, my package is with high priority, give me certain priority.
Well, if it was not in real time, you were just transmitting data from, say, a live show to a studio, where they were going to master that particular show, and it wasn't important you listen to it in real time. Would this system work for that?
If you record the file and then download the file, sure. What I'm hearing is anything that you're doing over Wi-Fi now, you would do over this.
Right.
Actually, I thought you said the Wi-Fi has a bigger bandwidth or whatever, but this is a lot narrower, so you might not be able to do all this kind of same stuff.
It is more available spectrum if you think of it, but the bandwidth, you can do similar things over this that you can do over Wi-Fi.
So my question is, what if, we don't have this mic, this illustrious mic protector that no longer doesn't exist yet, and might in 20 years for everybody. But a microphone comes in and it doesn't have any kind of indication. I mean, you could of course mess up the other mics that are already running, but does yours negotiate?
Yeah, I will definitely talk about that.
Good.
So I have, I think, 2 evaluation slides, and I'll talk exactly about deployment. So there's a couple interesting cases of deployment. So for evaluation, what we did here is we have the mobile microphone within 20 to 30 feet. And here on the x-axis, we have time. On the y-axis, we have Whitespace device spectrum. So this is how much of a single channel it's essentially using around the microphone, and essentially shows how it adapts. And so what we did through evaluation is we verified that through this entire process, we never created audio disruption on the microphone system. And as you can see over time, it is using a significant amount of the channel without ever actually interfering with that mic, right? And so the mobility of the mic here really did not hinder our ability to use that channel. We do adapt over time as the microphone signal adapts. But in doing so, we do not interfere with the mic. And so this was a more challenging scenario. In this case, we had a low-power microphone. And what we did is, moved around with the microphone, et cetera, and we allowed the SEISMIC-enabled Whitespace device to essentially use the spectrum. So in this top graph here, what we show here is the power of the microphone. This was recorded at the same time that we did the actual experimentation. And what we do is we plot the amount of frequency we use with it. And so over time, essentially, this microphone is fluctuating. And what we do here is we have something that's called like a lower bound on our threshold here, where this microphone essentially kicks itself into low power mode. It's essentially the mic protector says, like, hey, the microphone power at the mic receiver is so low that we are basically going to introduce a low power mode, where any sort of ramp ups from Whitespace devices or anything could possibly cause interference with the microphone, and we do not want that. And so in these cases, the Whitespace device essentially has to vacate the channel. And so this is to provide essentially that extreme protection over the microphone, right? And so over time, what we show is that the Whitespace device adapts frequency. It uses the channel. When the microphone power is significantly low enough, we choose protection over the microphone and essentially vacate the channel.
And that will be acceptable to the users and providers of this service.
Yeah. Right. It's opportunistic spectrum access, so we want to use it while it's available. Right. So what we did for an evaluation with many microphones. So we haven't gotten a chance to test this in a live environment. But what we did do is we were able to talk to some coordinators from various events and receive microphone data. And this is essentially where microphones are placed in the frequency domain. And from this, essentially drive a simulation in which we can essentially use the real microphone placement from the 2008 NBA All-Star Game, 2010 BCS Championship Bowl, and the 2010 Worldwide Partner Conference. So this has a various number of mics between these events. And so what we do is we essentially model signal strengths of mics to mic receivers, model interference powers of Whitespace devices, and essentially simulate 1,000 SEISMIC-enabled Whitespace devices at each event, and ask the question, if a Whitespace device was at these events, essentially how much spectrum could it use based on all of these microphones? Okay, so what we do is we present the evaluation, and we compare it to essentially 3 different things. So again, we knew the mic placement of each of the mics across the events. And what we have here in the red is if we followed the FCC ruling and essentially vacated a channel because a microphone is there, how much spectrum we actually end up having. And so on the y-axis, we have available spectrum in terms of megahertz. And based on that, this first bullet point here shows that if we followed the FCC regulation, essentially at the NBA event, we would have 1 free channel. At the BCS Bowl, 7 free channels. And at the Worldwide Partner Conference, 17 free channels. But now what we do is we compare it to if your Whitespace device was SEISMIC enabled along with the microphones. And if you look at essentially these green bars here, this is how much the average SEISMIC enabled Whitespace device would be able to achieve in terms of spectrum availability. And so this is essentially achieved by suppressing frequency around the microphones, leveraging the fact that the interference from the Whitespace device isn't always going to require suppression because it's below essentially the squelch tones. You're not going to interfere with every single microphone, right? And so we're taking into consideration essentially spatial awareness. And then essentially what we did is we also present the optimal suppression. So let's say sub-carry suppression was perfect. We could suppress exactly within the frequency band. We're actually pretty close to that value. And then so finally what we did is we said, OK, we have 1,000 Whitespace devices. Essentially, what amount of available spectrum do these devices have? So for example, at the NBA event, 50% of these clients had at least 130 megahertz. And only 5% of these had less than 50 megahertz. These are essentially clients that would be either close to mic receivers, essentially have a lot of microphones near them, et cetera. So likewise, the BCS Bowl, 80% of clients had more than 130 megahertz, and WPC, 90% had more than 145 megahertz. Sure.
Question, how does that translate into data rate?
So data rate, so that's all going to essentially depend on the modulation you use, something. So if you compare it to something like 802.11g, so or even N, let's say you get 128 megabits per second over, let's say, a 20 megahertz channel or something like that. So you could essentially divide this by the number of channels you would achieve, and then essentially multiply that data rate by your spectrum, right?
Roughly 7 bits per hertz.
Okay.
So right now, so what John was saying was for 2x2 MIMO. If you have a single antenna, it's 3.5, 3.6 bits per second per hertz.
So 50 megahertz is 150 megabits per second.
Yeah.
And how many Whitespaces devices does that translate into? How many can use that at the same time?
So again, this all operates by I transmit, then you transmit. Essentially, we carrier sense. So based on that, what you end up doing is you do a fair share. Because you have to alternate between transmitting, that essentially is a fraction of the number of devices in that spectrum.
What fraction?
So if you had, let's say 100 devices in the spectrum, that fraction of airtime is essentially divided by 100, a little bit additional loss due to what's called back off. We need to listen and then transmit, et cetera. So it's all relative to the number of actual devices.
So with this amount of available space, how many devices can fit into each one?
I mean, how many? It's just how fast will they work?
Yeah, exactly. You can pack.
How slow are you willing to go?
So at full speed, how many will work?
Well, depends what is full speed. So
20. What would Ivan
so with
just say?
Wi-Fi, Wi-Fi uses 20 megahertz mostly.
Yeah.
So if you could fit in 4 Wi-Fi networks.
So 1,000 devices roughly will have 1 megabit per second access to internet if they do it constantly.
If everybody's trying to stream.
Is everybody basically tries to look at the TV transmission, which is not quite good, but it's still tolerable, considering the fact that most of them will be in the pockets of their owners.
So if 1,000 can do 1 megabit per second, then 20 megabits per second is the maximum possible? Is that what you said?
Oh, it depends. Even in this building, our network goes to 300, 480 megabits per second, the wireless network. It depends on.
So it's going to be a direct mathematical relationship there between.
So they share the bandwidth.
Yeah.
You have 150 megahertz roughly, divided by 1000, it's 150 kilohertz.
Yeah.
Multiplied by 3-4 bits per hertz, you're at 0.6 megabits per second.
So at the NBA game, which is in a 15,000 seat arena, you can't have 15,000.
But not everyone will be using it.
That
Someone will be watching the
will not
game.
be in the microphones in this case.
Someone will be watching the game. A few people will check emails.
That's how it works now.
But if
those 15,000 take out their devices and start to stream, the network will collapse without microphones.
But if the usability of these new devices is so poor that nobody will want it, that takes care of the problem.
That was a very audio engineering stuff.
Yeah. That's why we had the first slide telling you why Whitespace is important.
Okay.
So this was a question that came up. Deploying SEISMIC. This is actually a great question. How do you actually deploy SEISMIC, right? So essentially, let's take the scenario that was given. So some microphone has the mic protector, some microphone does not. If the Whitespace device is assuming everybody has a mic protector, it's going to start to ramp up. The one's going to strobe at it, the other one's not. And it's essentially going to trample that other microphone, right? So how do we actually partially deploy SEISMIC? So the first thing that we can do to deploy this optimal SEISMIC protocol, I'll talk about another way of doing deployment, is that the mic has to report to the database if it has a mic protector paired with it. And so by doing this, essentially, what a Whitespace device will do is when it enters a channel, it checks the database. If every microphone in that channel has a mic protector, it can perform the SEISMIC protocol. If any microphone does not, it cannot, and it has to vacate that channel to essentially protect that one microphone. So this would essentially be a way of partially deploying SEISMIC. And so essentially by doing that, you would provide protection for the non-SEISMIC enabled mic systems and still allow convergence to using the spectrum around those who do.
But only in a long-term installed microphone system, not a portable. It's not going to get in time. It's not going to get in the database if I put it in tonight.
No, it will.
It's going to get in the database.
Yeah, it definitely will. So once you enter in that database, then essentially the Whitespace device is going to check that database before transmitting.
So if I turn on a microphone tonight, it goes into the database tonight, and
Correct.
somebody else can see it tonight.
Right.
Under the database, you're purporting, not necessarily the FCC's mandated database.
Correct.
Oh, so you got to differentiate there between those two databases. Okay. So there's a local database that it's consulting, and there's a
No, so
regional
ideally we
database.
want, so with SEISMIC, we would expect the FCC database to be enhanced to this much.
Yeah,
The
to essentially
FCC
support
now
this
requires-
Yeah.
The FCC right now has the mic data, but there are changes. For example, right now it requires Whitespace devices to consult with the database
Right.
once every 24 hours, or if it moves more than 100 meters.
Right, but the database, you have to tell that database 30 days in advance of when you're going to use it, that you're going to use it.
That's if you're
The
using
FCC database.
Yeah, yeah.
But you're saying there's a local database.
They're
as well.
proposing a different database.
We are proposing
Yes.
modifications to that database,
Yes.
enhancing that database.
Yes. So if this is accepted, there will be two
Right.
databases.
No.
It'll be one, but it'll be augmented with the new
So
information.
this would be a way in which existing mics can continue to use other channels beyond the two channels,
Yes.
where what they do is they can populate their entry,
Yes.
and then Whitespace devices will talk the SEISMIC protocol beyond that, after that.
Okay. Thank you.
So there's one more sort of deployment scenario, which I'll just summarize as an easier to deploy. It's less optimal, but also less complex. So essentially, what this deployment could do is not use some of the more complex sides of SEISMIC, like this power ramping, right? So essentially what we need to do when we enter a channel is we simply power ramp, right? And essentially we could remove some of the interference detection at the mic system. So if you remember, there were essentially two components that we needed to know to do suppression. One was the mic signal at the mic receiver, and one was our interference level at the mic receiver. So there's actually another way to build a sort of a different flavor of SEISMIC. And the way to do this is essentially the following. So remember, there are the two key things needed. But what we can do is the following. So to learn the mic signal power, what we can actually do is use the database to update essentially the entry for the microphone to include the mic signal power, or is essentially a range of signal powers over time, right? Essentially some average signal power, some lower bounds, et cetera, so that we know approximately how this mic is operating. But then also we need to know essentially the amount of white space device interference on the mic receiver. So something else that you could do here is enable essentially the mic receiver as a beaconer. And essentially if the mic receiver is periodically beaconing, transmitting, et cetera, what you can do is leverage that to estimate your interference by using channel reciprocity. So I can say the approximate signal strength of the mic receiver to me is X. Therefore, I can estimate based on that approximately what my interference power on the microphone receiver would be. And so by doing this, you could essentially use these two values to use a more conservative suppression to avoid interference with the microphone, but possibly remove some of the complexity of SEISMIC. And this could be another possible deployment scenario. So sort of in this optimal SEISMIC protocol deployment, we achieve the highest available spectrum efficiency. This is really a scientific contribution of our work. We require a little more complexity at the white space device and mic, and a number of modifications are essentially needed for deployment. The beaconer and the database approach could essentially enable a less complex SEISMIC protocol. It's essentially easier to deploy, fewer changes are needed, but you don't achieve this optimal suppression because you have to essentially take more conservative suppression values to avoid interference with the microphone. But it's a way to possibly approximate it. So in summary, from our talk, what we've shown, the most important thing here is that microphones and white space devices can coexist on a TV channel. There's really no need to essentially have these extremely conservative rules that essentially say we cannot coexist on a channel, we need to essentially reserve channels, et cetera. So we proposed the SEISMIC system, which required no changes to existing mic systems. So your mic systems can operate as is. You can augment it with a mic protector, and it could be possibly built into future mic systems. And by doing so, we essentially ensure maximum spectral reuse of white space devices of the spectrum surrounding the microphone. So that concludes my talk. I'd like to thank everybody for attending. Thank Ranveer for talking, Ivan for hosting, everybody else for basically making this happen. And if you have any other questions, the floor is yours.
Is there enough difference in the complexity between the full system and the light system that the manufacturers may just say, well, the light system's good enough and it's a whole lot cheaper, we're just going to go that way and forget the complex system?
It could be, in the sense that you avoid doing this power ramping by entering the spectrum, right? And so maybe they say that doing this is a little more complex. Maybe there's some error in doing it, something like that, where maybe the spectrum you gain is maybe not as beneficial to just doing the basic protocol.
The degree of extra complexity, is the full system twice as complex or just a few percent more complex? Is it going to cost double as much to implement the full system?
The thing is, everything has to be connected to the internet.
Yeah.
In the partial system. But it doesn't have to do interference detection anymore. It's constantly just speaking.
Right. Yeah,
So
so
that's why it's very
Okay,
trivial.
so it's the
It's trivial to
connection
implement,
straight,
but
okay.
it needs to be connected to the internet. That is an assumption which we don't know how reasonable that is. At all events, is it easy to connect the mic receiver to the internet? And what's the added cost?
And backing up way on this, the frequencies that you're talking about this affecting is it correct that they're not the two channels above and below channel 37 that
We're
are
talking about
reserved
channels.
for microphone use? So right now, you cannot use those two channels for data transmission. It's reserved for microphone use. And you're not suggesting using those channels for this?
So we are saying be more general. Why just reserve two? That is, operate anywhere. Whitespace devices will just configure around you, wherever you want.
Yeah, their goal is to change the policy, Dan. They want those channels.
Yeah.
Okay.
So that's the whole goal of this.
Okay.
So the principle on which SEISMIC is based is that as long as you don't overpower the squelch tones, then you don't interfere with the audio.
correct.
Under which channel model is that valid?
Right, so this is essentially leveraging FM capture, where if you think about how, I'm not sure how familiar you are with FM modulation and demodulation, but essentially what you're doing is you're doing frequency variations, right? So you have some tone and you're varying the frequency at which it operates.
I'm referring to the channel model of the wireless channel. I wasn't asking.
Oh, no, this is the receiver's view. This is purely the receiver's view.
Just
irrespective of the channel model.
Right.
We're just looking at what is being received at the receiver and what is the impact on the. So the way we measure it is, we are taking an input from an antenna, putting it through a splitter. One part is going to the receiver, the other part is going to the spectrum analyzer. So we are getting the exact view that the receiver is seeing, and from that we are inferring when do we get interference, when do we not.
Right. So it's fair to say that that's good enough. So in SEISMIC, you set a power threshold, so that you detect the noise floor to see if it's above a certain range. If it exceeds that threshold, then you start beaconing. How do you adjust the power of your beacons to accommodate the effects of the wireless channel? So, for example, what happens if the white noise device, what if that sender just happens to be in a fade where it can't actually hear your beacon signals?
Yeah, no, that's a valid question. So that's in terms of being able to detect the strobe signals, right?
That's right.
And right,
It
so
will be able to hear its own transmission.
Right, but you have to understand that the wireless channel is not a bidirectional channel. It's not a symmetric bidirectional channel. That is the nature of a wireless channel.
But the fades are, the assumption is the fades are not really deep fades lasting seconds, right? Most of the fades are short-term fades. Those are the fades that can be handled. Right? It's the extreme long fades which are very rare. Those don't usually happen. So a few seconds, yeah, that's something which we can. There can be periods where for a few seconds.
It could be a shadow.
It could be. The shadowing case is. This is you're saying for the Whitespace device
That's
being
right.
in the shadow
That's right.
region.
So how do we know that the beacon we're sending out is strong enough to overcome any shadows?
We're just relying on the multipath working here. That is, anything we send, either direct or through multipath, gets to the Whitespace receiver. And the point is, the strobes, the other thing is the strobes are sent at much higher power than we expect these portable Whitespace devices to be using. Right? So the FCC specifies 40 milliwatts for portable devices. These strobes are sent at much higher power, more than 100 milliwatts. Right? Narrow band, really high power. So those are the ways we plan to compensate. We haven't seen a case where, because of this power asymmetry, you would be countering most of those scenarios.
You say that no change is needed to existing mics, but that's really only under the database model. I mean, just strictly without some sort of augmentation with with a protector.
Right. So what we're saying is that you don't need to make hardware modifications to the mic system. And so...
The mic protector.
Yeah.
You do need to augment the system in some way.
Right. Correct.
Okay. On the database paradigm, would it be reasonable to build up a database of the different microphone manufacturers' models? I would make it incumbent upon the wireless manufacturers to provide that data, so that a user, when entering their microphone, isn't simply saying, I want this channel, but I have this microphone model on this frequency, and then that way you could at least get down to knowing that I only need to take out 200 kilohertz or whatever.
Right. Yeah, essentially by providing that information, we could know, we could have a better estimate of how much we need to suppress, to be less conservative. Right.
We could, then with a database-only model, you would at least be able to recapture more of the spectrum.
Right.
I mean, the main thing is, our company, we deal with a lot of houses of worship. And the average house of worship doesn't even know there's a database yet. And it would be a stretch to get them to even look at their microphone and figure out what the frequency is. But maybe we could get them to say, okay, yes, I have this model XYZ, and it's I see this 247 megahertz number on it, and we could get them to do that at least to help with that.
So I'm not sure I understood the answer to the question you gave. I'm concerned about that like he was saying, houses of worship, karaoke, the bar next door to your building. They're going to have a concert tonight, and they just turn on their wireless microphone. And you said something about the microphone has to notify and whatever, and if it doesn't do what it's supposed to be doing, it has to vacate the channel or whatever. So the bar is not going to be able to use it. They're going to have to find another channel. Or
so
I'm confused about what this,
okay, sure.
This
so
must thing sounds like it's going to, actually have to change a lot of the infrastructure of what's being used commonly around the city in the way of wireless microphones, eventually. Once you guys get control over all these extra channels.
What was the must around again?
I don't know, you said something, it was actually on the slide, it said that the microphone must do this, and then you said that if it doesn't do this, then it must vacate. It can't use that channel. A new microphone coming in.
Not the microphone, the Whitespace device.
Yeah.
Whitespace device?
That's the purpose of all this, is to make the Whitespace get out of the way of the mic.
Oh, I got it backwards.
Yeah, the other way.
So my question was, and I thought your answer, maybe I misunderstood.
Yeah, sure.
A new microphone comes in, so your thing is going to look at that and go, okay, we need to, it's going to be looking for new microphones all the time, even if they don't have a mic protector, correct?
So if they do not have a mic protector in this partial deployment situation, that mic needs to basically notify the database that it's a mic in the channel that does not have a mic protector. It does not follow SEISMIC.
Well, that's what I'm not understanding, is some guy at the bar isn't going to be notifying anybody of anything. He's just going to turn on his karaoke system.
Well, by doing this, right, so what the FCC is mandating is that this mic has to update the database, right? So it's basically part of the rules, right, where right now, essentially, if a mic's operating, it needs to update the database of where it's operating in to have the protection.
Okay, but you guys are going to assume that there are going to be a lot of people who aren't going to follow that, and they're going to just turn on their microphone and do whatever the heck they want.
No, what we are doing
so
is...
your data system's got to negotiate and figure that out so you don't lose data or lose something weird, right?
No, so Ivan put it right. We are not taking away the frequencies. We are returning the frequencies to the audio guys. Right now, you wouldn't be able to operate your mic anywhere on any channel. That's it. It'll be illegal if you start operating it on any other channel other than the two channels.
Right, but if you
so in order to enable that, what we are suggesting is, well, keep the systems as they are. Don't educate all the mic people again. Give this extra box. You just plug in next to your mic receiver, and your system starts working as is. The new devices, it's on them to adapt and make sure that they are not using the frequency.
Right, but to protect yourselves, you have to protect your data, so you should be constantly checking just to
So the
make
way
sure,
we
right?
protect our data, so this extra device that you put in is the one that's going to update the database. It's the one that is going to signal to the Whitespace devices, hey, move out of this frequency.
Even if somebody didn't notify the database, they just turn on their mic,
We have a disagreement on that
Okay.
subject there.
Mhm.
The two channels above and below 37 are open to wireless mics.
Yeah,
Period.
reserved for
Now,
wireless
mics.
reserved for wireless mics. And any
And there are
other
others
space
that are
below 700 is open to wireless mics as long as it doesn't
up to
interfere.
700.
Up to below 700.
Yeah, 470 to 698, we can go anywhere there's not a
Anywhere
TV
in
And
there.
VHF.
Yeah, but you're
Without-
not guaranteed any protection.
You're not guaranteed any
Whitespace
protection.
devices could come and trample and you could hear
But
the
it's not
audio sound.
illegal. It's not illegal
It's
for
not,
us.
it's
to
not
go-
illegal, you'd hear the same sound. You'll start hearing
Yeah.
the same sound
Yeah.
that
Take
you
the
heard.
chances to be just.
Yes, but it's not illegal.
It's not
for
illegal,
us
that
to
was,
go there.
yeah, but you'd hear that interference, at which point
Yes.
it's as good as unusable.
Interference from whatever source,
From Whitespace devices, they could come and start
which,
interfering.
well, they don't exist yet, but when they do, yes.
It'll become unusable, right? So that's why.
Right.
Except that your Whitespace's devices are mandated to avoid existing uses in those.
No, no. In those frequencies, right now with the latest ruling, they're not required to sense at all. So you're not sensing for wireless mics. You can, Whitespace devices can operate on that frequency, go right over the mic without even listening to it.
It's up to us to,
They've been working on it, but
yeah, it's up to us to move into the reserved channels. And the whole purpose of the database at the moment is, if you know that on December 19th, you're gonna need, let's say 36 channels, and whatever you have only gets you 20 channels on the reserved channels, then you have to reserve the extra space. And that's when these devices are supposed to query the database, figure out that you're there, and go somewhere else. That's how it's supposed to work right
You
now.
alluded to another thing, it is, by the FCC mandate, we are required to use the two channels and fill them up and use everything we can before you're even allowed to go looking in the other
Right,
channels.
you have to certify that you have used up your reserved channels, and they expect you to get at least 6 mics on a reserved channel. So that's going to mandate a certain level of technology, because, you know, there could be anywhere from 2 to 12 channels of wireless mics on one TV channel, depending on the quality of the equipment. So,
Go ahead.
sorry, I'm done.
Well, I was going to make an additional comment. One thing that concerns me is we're discussing unlicensed Whitespace devices, in essence, consumer devices. And invariably, consumer devices, you're going to have companies that are not so considerate as Microsoft, trying to build as cheap as they can, with the cheapest chips they can, the cheapest sensors they can. And even though they're supposed to comply with all the regulations, that they're still going to tromp on it. I just see that happening somewhere down the road. And it's not something that you can specifically address. It is a concern from the audio side that I see interference coming from just that reality.
The thing is, here though, we would expect, if, depending on how much of it gets into the routing, these devices, if they're FCC certified, they would have to meet certain tests.
I understand that, and I've heard lots of other rules that.
Right, so it
that you
depends
get
what
tests.
goes in the ruling and what is part of other standards, right?
Sure.
So depending on that, at least a certain bar will be met. For example, for Wi-Fi devices, they do meet a certain bar.
Just in the real world, you know, I'll pick on Chinese manufacturers figures, well, I'll fudge the line a little bit here and dump them, and they've made their money before they even face any lawsuits or the FCC saying you can't do these anymore, and the devices are already out there, and there's nothing you can do about it at that point. I mean, and again, I understand, you're taking every precaution you can. You are addressing our concerns, and I appreciate that. I'm saying others would not be so considerate.
How are these devices doing their transmitting? Are they using, one device can talk to another without buying time from T-Mobile or AT&T or whoever?
The Whitespace.
The Whitespace.
Yeah, this is like
devices.
Wi-Fi.
These are all.
Anyone can use that.
Anyone can use it, so there's no overarching seller of that time and space. It's just the individual. Oh,
Yeah.
okay.
Quite attractive.
Yeah.
Do you anticipate this being a corporate or even a, say, really consumer, let's say, I mean, just, I have a big family and I have a big area that I want to just put out base stations and I just mount them wherever, or do you see this more as a, Verizon is going to implement a citywide
So there are
mesh?
different standards. So there's 802.11 AF, which is essentially Wi-Fi plus if you think of it that way. right? Like you had Wi-Fi 11N with more speed. 11AF is Wi-Fi on this spectrum, which should be like you buy your home router and you plug it in you buy it from Best Buy, and it just does white spaces. You can cover your entire house using your home router now, which you couldn't do otherwise. That's one scenario. The other standard that is being developed is 802.22, which is for regional area networks. That is, I want to cover entire city. Then what protocol should they? That's more WiMAX like, while 802.11AF is Wi-Fi. So they are both scenarios that are in consideration.
In the same frequency bands.
Yeah. The other one, which is more likely to come up, is M2M, M2M, machine-to-machine scenarios. Like my smart meter at home talks to the utilities and updates the data, those kinds of stuff.
Any other questions before we call it a night? Thanks to our presenters.
Thank you.